It's been exactly 9 months since I first took of what's known as the PhD qualifying exam for my PhD in machine learning. My program is quite unique in many respects, but maybe every PhD program is. One thing though that is common across these programs is that at some point, maybe the first or second year, you have to take a qualifying examination to qualify you in the program. This examination basically says you're ready to start doing research. In my case, this was an 8-hour examination that included probability, statistical theory, and machine learning. We get 2 attempts to pass the exam, and if we don't pass it, we get kicked out of the program, with an option for a master's degree. I already have a master's degree, so that was not really an option. Last year, I spent my entire summer preparing for this exam. In this video, I want to show you what the statistical portion of the exam looked like. So this is the exam. As I mentioned, there are multiple parts to this exam, and this is just one of them. This is the statistical theory portion. For this part, we get 4 hours from 9 a.m. to 1 p.m. with no breaks. The exam is largely based on this master's level book. When I first started learning from this book, I did not like it, but as years progressed, I really started to understand why our professors chose this book to teach us statistical theory. The exam covers the first 9 chapters of the book, and the book really starts from the axioms of probability in chapter 1, random variables and their transformations in chapter 2 and 4. Chapter 5 and 6 are about sampling and data reduction theorems. The last 3 chapters are about statistical inference. Chapter 7 covers point estimations such as the Bayes estimator and the maximal likelihood principle. Chapters 8 and 9 are all about hypothesis testing and how to construct confidence intervals. So those are the topics that are tested for the most part. So let's take a look at the exam. So this is the exam, and when you first open it, you're greeted by this page that tells you how many points each question is worth. And as you can see, each question is worth the same amount of points. They are weighted equally, 20 points each. I won't go through the questions in order, but rather when I took the exam, I would first go through it and then identify the questions that are the most difficult and the easiest. And I will first start with the easiest questions. That way, even if I get stuck later on, I would have completed a fair amount of questions already. So let's start with question 9. So this is question 9. Let x be a continuous random variable with this PDF, a probability density function, where this PDF is parameterized by 2 values, alpha and beta. And these 2 numbers are positive real numbers, but they are unknown. And we're asked to derive this transformation, and we're also asked to state the support of y. So immediately, I recognize this as a chapter 2 problem, a transformation of a random variable. Basically, we're mapping the space from x to y under the given transformation, and then accounting for the fact that under the new transformation, the area under the curve also will have to integrate to 1, given that's a PDF. So let me show you the solution. The first thing that we have to check is that the function that's given is monotonically increasing or decreasing. That way, we can directly apply a theorem from the book that says that with the inverse of the transformation and some scaling factor based on their derivative, we can plug in the numbers and get an expression for the PDF of y. And then we can state the support, which is the y such that y is positive. And that is the result. Honestly, this question was as straightforward as it gets. And so this is the type of questions that I like to do first when I'm taking an exam like this. Another question that was simple but very interesting was the Bayesian estimator question. This was question 5. The Bayesian approach to statistics is fundamentally different from the classical approach. In classical statistics, all parameters are treated as unknown but fixed quantities. Bayesian inference combines both the prior belief about a parameter and the data that's observed from the sample to come up with a new belief called the posterior distribution to make inferences. So let's take a read at problem 5. Given a parameter theta and a random sample of n numbers that are independently and identically distributed from a population PDF given here, we now let theta, the parameter, have a distribution itself given by this gamma distribution parameterized by alpha and beta, both positive real numbers. And we need to find the Bayes estimator for theta. Let's take a look at the answer. As I mentioned, all Bayesian inference reduces to computing a posterior distribution. The formula for the posterior is the likelihood times the prior divided by the marginal distribution of x. To solve this, The first step is to calculate the likelihood. The likelihood is just the product of the individual PDFs of X because of independence. The prior is given by the problem and is a gamma distribution with parameters alpha and beta. Thankfully, the posterior is proportional to the product of the likelihood times the prior distribution. This saves us the computation of the marginal. If we carry out this multiplication, and after a bit of algebra, we're left with this distribution. It may not be apparent, but this distribution is the same as the prior distribution with different parameters. Instead of being beta, the parameter, it's now beta plus the summation of natural logarithms of xi's. The fact that we had a gamma prior distribution and ended up with a gamma posterior distribution is what Bayesian statisticians call a conjugate prior. This is a beautiful result. By doing Bayesian, we incorporate subjective belief and inform our beliefs with the sample to make inferences. As you can see, the final solution now contains information about the prior, alpha and beta, but it also contains information from the sample and the summation of the natural logarithms of xi's. And that is the answer. If you've made it this far into the video, you're probably thinking two things. One, why don't I give this video a thumbs up so that other people can enjoy this content? So go ahead and give it a like. And two, these problems are not that difficult. And you'd be correct. These problems are on the easier side. And now let me show you a more difficult problem about the likelihood ratio test. Problem 3 is about likelihood ratio tests. Likelihood ratio tests are a very important part of statistics because given any PDF, we can compute a likelihood, and with the likelihood, we can derive the test. And so let's read the problem. Let x1 through xn denote a random sample of size n from a population PDF given here. Note that the population PDF has an indicator function that depends on the parameter theta. And this parameter theta can be any real number. We have to now derive the likelihood ratio test of two hypotheses. The null hypothesis is that theta is 0 versus the alternative that theta is not 0. In terms of the test statistic, x sub 1, and in this case, this means the minimum of the xi's, so the minimum of the sample. You may use without proof that the unrestricted MLE of theta is theta hat equals to the minimum of the xi's. Why the minimum of the xi's, you might ask? I'll give you a hand wavy argument here, but as you can see, the indicator function depends on theta. This means that there is no x that is going to be less than theta in the sample. If you let this sample size go to infinity, it's very likely that at some point you will have an x value that is very close to theta. And in fact, the minimum of the xi's is going to be the closest to theta. And because this is a more difficult problem, I like to rewrite the question in my own terms. And the solution is going to be a multi-part solution. The first thing that we need to do for this solution is to identify the likelihood, as always. And the likelihood by independence is going to be the product of the individual PDFs of X. And we get to this expression. Then we have to identify the hypothesis space. The entire hypothesis space is all of the real numbers, but we have to partition this hypothesis space into the null hypothesis space and the complement of that. The null hypothesis space is theta equals 0, and the complement is all of the other numbers that are not 0. So this disjoint set. This disjoint set complicates things, and that's why we have this algebra down here. The next step in the process is to derive a test statistic that depends on the sample. The test statistic is the ratio of two maximum likelihoods. The first one is the maximum likelihood when the parameter is 0, and the other maximum likelihood is where the parameter is in the entire hypothesis space. This ratio will be a number between 0 and 1 and will be very large when the null hypothesis is true. Plugging in some of these numbers, we get the following, and we have to account for the fact that the complement of the hypothesis space is a disjunct set. To derive the test, we have to account for all of those scenarios, and we arrive to this conclusion. And this conclusion is intuitively saying two things. One, that if the minimum of the xi's is less than 0, we will reject the hypothesis. And also, If the minimum of the xi's is greater than some number that depends on the sample, we will also reject the hypothesis in favor of the alternative. And that's how you construct a likelihood ratio test. As you can imagine, missing one of these sets at the start of the problem will result in a miscalculation and therefore the incorrect solution. So far, I've shown you 3 problems with increasing difficulty. Even with these 3, you can get a good sense of how difficult the exam was. However, I will now show you what, in my opinion, is the most difficult problem in this exam, and that's problem 1. Problem 1 is about the shortest pivotal interval. The reason this is the most difficult is because it's 1, relatively unintuitive, and 2, it requires a solid knowledge on all of the previous chapters, but it also requires to do integration and optimization all in one problem. Finally, this topic is not covered in class. The professor expects us to read the book, and based on our interpretation of the book, we need to find a solution with no flaws. Let x, 1 through xn, be IID observations from a distribution with a given PDF, where theta is a positive real but unknown value. Find the shortest pivotal interval of theta based on this pivotal quantity, where x sub 1 is also, as in the previous problem, the minimum of the xi's here, with confidence 1 minus alpha, where they're giving us the transformation of the pivotal interval and its PDF. So the pivotal quantity concept goes back to the Fisher days in the 1930s, and it is a way of constructing confidence intervals in such a way that the distribution of the interval is independent from the unknown parameter theta. As we can see in the PDF of Z, it does not mention theta in any of these expressions, and that's exactly what we want. So let's take a look at the answer. Again, with these type of problems, I like to rewrite the questions, and then let's look into the solution. We need to find some A and B such that the probability of the pivotal quantity being inside those numbers is equal to 1 minus alpha. By definition, that's the integral between A and B of the given PDF. However, we need to find the shortest length pivotal interval, and that means we need to optimize these bounds. Now, this is a minimization problem with respect to A and B. After doing the optimization based on the derivative, we find an expression in terms of A, and that is the answer to a shortest pivotal interval question. With these questions, I hope I gave you a good sense of what my PhD qualifying exam looked like. If you enjoyed the content, consider subscribing and see you in the next one.